Okay, welcome to class. We have an exam coming up, exam 2, and I have some comments on that. But before we do that, I want to make a few remarks on homework for the weekend. We're going to have a fairly sizable set of homework over the weekend, and I want to go through the specifics of it with you right now before we start lecture. And that way we won't be rushing too badly at the end of lecture. So first of all, homework 12 will activate right after lecture today. And it has some concept questions and some calculations based on what we do today. And the last thing that we do today is going to be a calculation that I will record into a talking PDF file, and we'll work it out on the document cam, so you can take notes as we go, but you'll need that for the homework 12. In addition, I have another mini review homework set up that includes the Space Jam emergency, which is a set of problems involving free fall on another planet. There'll be some other review calculations like boxcars, etc. And there'll be some thermal energy items as well. And that is not ready, but it's going to activate 1 p.m. Friday, so you'll be able to tackle it at that point. Okay, so that's the homework situation. And for studying purposes, just read everything. Study everything. Chapters, additional readings, Twitter, the Twitter notes that we have streaming, discussions as well. And by the way, with the homework assignment set this weekend, you're going to experience a high probability of getting stumped. All right? And if that happens to you, I highly encourage you to post something in discussions, a question, and make it as specific as you can. Don't just make the title, "Help me," but say, homework 12, how do you get number 7 free fall speed? Or something like that. And then post your question. All right, another thing that I want to bring to your attention is the YouTubes. I videotaped or I video recorded the 2 demonstrations we did Thursday. Here's David. Yay. And he's up on YouTube, and Ashley's up on YouTube, and so are Stefan and Miss Vanessa from the first lecture. So you can look at those. And by the way, you might want to make a note. The demonstration video with Stefan and the one from noon lecture with David, I added some extra notation in the Chiron strip at the bottom of the video to instruct you and give you notes basically on what was happening in terms of the exchange of angular momentum. So you may find it to be helpful to reinforce the idea of angular momentum conservation to look at that second demonstration especially. Right? David's and Stefan's, and they're in YouTube. All right, about exam 2, a few comments. Exam 2, just be ready for everything. And in other words, lectures up to and including today's, lecture 16. Roughly chapters 4, 5, and 6. But in reality, we're not going to stop talking about F equals ma for the rest of the semester, or velocities. So effectively, it goes all the way back to the beginning. All the homework except homework 0, of course, is basis for studying. As always, bring the following: a raspberry-colored UCF Scantron with the Pegasus logo, your iClicker 2, and I have the list of the students that forgot last time, and I'm going to be looking for you. Make sure you Don't forget your iClicker again, right? Number 2, pencil and a good eraser, of course, for the Scantron. Bring your calculator. And it can be a little $15 scientific calculator from the bookstore. They have got buku calculators over there. Go get you one. And for once, it's not a bad price for something at the bookstore. Did you ever notice it? You know what, you guys? If you buy my e-textbook from the publisher, what is it, like $85? All right. And what is it at the bookstore? Like 100 and something? 120. It's ridiculous. You know, the price gouging. Maybe I shouldn't know. Anybody here work at the bookstore? One person. Okay, are you going to narc on me? Okay. I mean, the bookstore is... I have a lot of conflicting feelings about the bookstore. I mean, they have Starbucks, but then they also have those prices that they gouge people with. Anyways. But anyways, the calculators are pretty cheap over there. And you may not use your cell phone for any reason, so don't take it out. And you'll be able to do everything longhand. It shouldn't be a problem, but try to bring a calculator if you have one. Okay, now that's exam 2. And just be here, and we're going to have a similar seating situation, okay, as last time. Except I think the front row is going to be a different group of seniors. I haven't figured out who that's going to be. Last time it was senior psych majors, but I think it'll be somebody else next Tuesday. Anyways, now, final note for the good of the order. I'm going to update the clicking summaries either today or tomorrow. I have to go to a Windows computer to do that. And that will allow you to figure out the estimate or make an estimate of your semester grade. If you look at your clicking, and then you also have to add up how many points you've earned from the homeworks, except for homework 0, and then put it together the way that I specify in the syllabus. So keep an eye on discussions. When I post the new clicking summaries up to today and including today, hopefully tonight or maybe tomorrow, you'll be able to do your grades. And the reason I know that some of you are concerned about that, I think a few of you may be considering a W, and you don't want to do a W if you're actually doing fairly good, all right? And so that'll be helpful for you. Good. Any questions about any of that stuff? Taylor, are you good? Oh, I saw your hand go up there. Okay. All right, let's keep going. I want to talk some more about heat energy. And this diagram from page 98, I really like it. I spent a lot of time figuring out a good way to it's my diagram, I made it. It models a molecule bouncing off the side of a container, a molecule in a collection of gas inside of a container and bouncing off. And as it bounces off the side, it transfers, or the wall and the molecule exchange momentum, delta P. And it turns out that the exchange of momentum can be summarized as pressure, a macroscopic pressure. You know, you go to the gas station to fill up your tires, you have to set it, 32 psi or whatever the pressure setting is for your tires. Okay? And that's similar to the idea that the average kinetic energy correlates to the temperature of a gas. And we'll talk about the formulas for both of those in just a minute. Let's keep looking at this diagram. There's delta P, and there's zillions of molecules in a gas. So if you have like a balloon or a scuba tank or any kind of a propane tank, anything like that, if there's gas in it, it's There's going to be zillions of molecules in there. And they're all going to be exchanging delta P with the wall. And there's going to be a certain number of delta P's per second. Now, delta P per second is a force. So those exchanges, those ricochets, be it at a straight in and straight back out kind of a ricochet, or any kind of an angle, kind of a glancing angle ricochet, they're all going to transfer a certain amount of delta P to the wall. And the wall is going to transfer the exact same amount back to the molecule, and it'll reverse course, as you can see in the diagram. Now, that delta P over delta T is a force. It's good. Well, when you think of all the molecules ricocheting off the wall, that'll translate to so many newtons of force. But the way that you have to figure out the pressure is by looking at every square centimeter, or every square meter, or every square inch. So the pressure is defined as the amount of force per unit area from all those ricochets. In the metric system, that would be so many newtons per square meter. In the English system that we use for car tires, bike tires, PSI, actually I see some tires marked in newtons per square meter. Anyways, English system, it's pounds per square inch, PSI. Right? So the idea is that every square meter or every square inch of wall gets a certain number of molecules banging into it every second. All right, that's a certain amount of delta P per second. And so the force per unit area, the pressure, is involved with those zillions and zillions of delta P's per square inch, or per square meter, or per square anything, per square light year. I'm sure astronomers do pressures in these gigantic molecular clouds, and that would be, it's not really contained in a container, but they still probably think in terms of light years because they're that big. The other thing that it has to do with is the spatial distribution of molecules. In other words, how many of them are actually in there adjacent to the wall? Okay, so the density of the gas encodes, every cubic centimeter of volume adjacent to the wall is going to have a certain number of molecules in there. And a bunch of those molecules are going to ricochet off the wall and give you a bunch of delta P's. So for every square centimeter of the wall, you're going to have a certain number of molecules adjacent to it. And that number of molecules depends on the density, or the density is the number of molecules per cubic centimeter adjacent to the wall. So that's how the spatial distribution, or the density, also enters the equation for pressure. Now, to do all this calculation for pressure, you have to do a zillion calculus, statistics, and trigonometry calculations. It's pretty tough. We're not going to go through all that, but we are going to go through the concepts, and I'm going to show you a couple of the equations. Let's do a clicker question together. Okay? See if you can think with your B-R-A-I-N. What did I say? Did I say Brian? No, I spelled brain. B-R. Dude, you totally juked me on that one. Gosh. What is this trick? Somebody already voted for. You don't even know what the question is. What are you doing? Look at these people voting. Gosh. Now you guys are blazing me up. All right. Here's your question. A dense gas, highly concentrated, compared to a sparse gas, very diluted. Right? Read carefully and make a decision. All right, good. Nobody's voting for E. And a bunch of you wiseacres voting for... No, don't do that. Good. Now you guys are playing with my mind. Goes with the last answer, yeah. So you could try to juke me. I could see it up here. But until I hit click, I won't. But actually, I can see the data records your first and your last.
Oh, really?
Yeah. So if you try to juke me with E on your first click, I'll know it. I'll be able to track you down like Chinatown. Yeah, all right, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Click. All right, you guys did good. Correct answer is more. Yeah, a dense gas will produce more collisions in every square centimeter of surface area. Because dense means there's more molecules there. So every cubic centimeter adjacent to the wall, it's loaded if it's a dense gas. If it's a diluted gas, you still got molecules in there, but not as many. So you're not going to get as many slam down interactions on the wall. Now, the other thing that I want to bring out to you is the fact that if the wall actually moves outward, then the gas will have done some work, F delta X. And you may think to yourself, Dr. B, how can a gas, how can all those little shrimpy molecules move a wall? Well, I'll give you an example. Every time you blow up a balloon for a birthday party or something, right? You're exerting pressure, you're increasing the pressure in the balloon, and when you blow in, and it gets harder and harder to do that, but the wall expands. Another pressure, another bit of work done by pressure, the piston inside your internal combustion engine. You detonate a little bit of gasoline vapor, expands the temperature, increases the pressure, and the piston moves up, or whatever direction the piston is designed to move. Now, all of this is based on the kinetic theory of gases. And the shorthand term that I like to use to describe the philosophy of the kinetic theory is e pluribus unum, from many, one. So the pluribus for temperature is the kinetic energies of zillions and zillions of molecules that you cannot see. They're submicroscopic. It's very hard to see a molecule, right? And so, but if you use F equals ma, 1 FmV squared, and a little bit of statistics, and a little bit of trig, and a little bit of calculus, you can figure out that the average kinetic energy, where's my cursor? Come on, baby. Here we go. Okay, in this right-hand cell, in the second row down, third row down, average kinetic energy is equal to 3/2 times a constant K times the temperature. So the temperature is the single macroscopic quantity that is correlated by this formula to the kinetic energies of all the zillions that you can't really track down. But you use math to summarize and get an average. Now, momentum exchange. The exchange of momentum, all those ricochets, yeah, that leads to pressure, delta P over delta T, yeah. And doing a lot of calculus and math and trig and stats, you come up with something called the ideal gas law. PV equals NKT. Now let me show you what K is equal to. K is called Boltzmann's constant. And it has this weird value, 1.38066 times 10 to the minus 23 joules per Kelvin. Capital N in the ideal gas law is the number of molecules in your container. In the ideal gas law, little p, lowercase p stands for pressure. Capital V stands for the volume. Go ahead and add that to your notes. In the ideal gas law, capital V stands for volume. So you have a container of gas. It has a pressure from all those delta P ricochets. And it has a volume. You can measure the volume somehow, with a ruler and so forth. And then it has a certain number of molecules in there. That's capital N. And you attach a thermometer in some way, Anthony, and you get a temperature, capital T, right? And this is the law called the ideal gas law that governs that. This is called an equation of state. And it relates the thermodynamic values of pressure, volume, number, and temperature. And there's a constant of nature in there called Boltzmann's constant. Students, side note, Boltzmann's constant, K, joules per Kelvin. Those are the units of entropy, E-N-T-R-O-P-Y. Raise your hand if you've ever heard anybody mention the word entropy or if you've read it. Okay, entropy. Okay, chemistry class talks about it a lot. Entropy. A lot of people equate the concept of entropy with disorder in a physical system, disorder in the universe. But there's a lot more to entropy than just that. Anyways, Boltzmann's constant, this mysterious constant of nature in the metric system, has units of joules per Kelvin and a value of 1.38066 times 10 to the minus 23. Now, we're not going to do any calculations with it, but we are going to think about these formulas here because Boltzmann's constant appears in both of them. And I'm sorry that these letters are a little dark. It looks very clear and nice on my computer, but I should have made these letters in white instead of black. Anyways, here's a picture of Boltzmann. E pluribus unum, thou good and faithful students. Yeah, he's the guy that developed this whole idea that you envision this gas of zillions of little particles, and they ricochet off each other, they ricochet off the wall, and they all about F equals ma, and doing all the trig, all the statistics, all the calculus is called statistical mechanics, and he's the guy that invented it. A very successful theory, proven many, many times. Now, before we go further, I want to review and recap the heat melt heat problem from homework 11 because I had a bunch of students say in office hours, Dr. B, I didn't quite get it. I'm missing something. And I saw a few people in discussions with the same thing. And let's recap the basic procedure. And we're going to go through the concepts here. And then we're going to go through the calculations that spring out of the concepts. All right? So, yeah.
There is a thing on the homework, questions on the homework that were about, I guess,
Mountain Dew.
no, specific heat and like whatever it takes to make 1 gram into a Kelvin. Those are different, specific heat and
There was a bunch of specific heat concepts in there.
they're 2 different things.
Specific heat and latent heat are different.
No,
Yeah.
but latent heat was the answer. Specific heat was the answer for the 1 gram to make it a Kelvin. And then calorie was the answer to make 1
Yeah,
cell.
calorie and specific heat. Specific heat of water defines the calorie. So yeah, they're kind of intertwined. And so thinking it through, Camille, is going to help you think quickly on the exam too. So I'm glad you did that. I'm glad you asked that question. Anyways, here's a specific example from homework 11. Given 7 grams of ice, and everybody started at 268 K, but everybody had different values of mass. In this example, it's 7 grams. And we want to heat it up to a liquid state at 276 target temperature, 276 Kelvin, all right? And everybody had a different target temperature, all right? Or every time you take it, it's possible to get a random number of final temperature. And so the question was, Given those specs, how much energy does it take? How many calories does it take to do that? So the first thing you have to do is heat the ice up to the melting point. You're trying to make it liquid at a certain temperature, but the first thing you got to do is get it to the melting point. All right, so in that part of the process, you use the formula Q equals mc delta T, because that's the heat up equation, the heating up formula. Or the cooling down formula if delta T was negative. Now, we use the mass, 7 grams, whatever it happens to be on your attempt. And we use the specific heat, Camille, 0.50. Now, that's the number that encodes how easy it is to heat up a single gram by a single Kelvin. Yeah, you got to be careful with it. But I usually write out the word calorie, C-A-L. But yeah, in textbooks and stuff, little c stands for a thermal calorie. Big C, capital C, stands for a food calorie. We'll talk about that in a minute. Question? Delta T could be negative if you're cooling something down. But this is a heating up process, so yeah. Right. That's the specific heat of H2O ice. Now, if you have CO2 ice, dry ice, it has a different specific heat. If you have a piece of iron, that has a different specific heat. If you have a diamond, that has a specific heat. If you have liquid nitrogen, that has a different specific heat. Depending, some substances might have similar values of specific heat, but you got to measure them all. Question? Remember 0.5? No, you're not going to need to remember that. It's going to be on a table on the cover page, so don't worry about it. But you're going to have to know how to use it.
Yeah.
And that's what.
Are you going to need to remember that it melts at 273?
No, the melting points. I'll have all that stuff on a table. All right. So you got to know how to think your way. Use the table as a tool. All right. The next thing you do, you heat it up 5 kelvins. Okay. Now you're at the melting point. So every calorie of additional heat, Camille, at this temperature melts something. It doesn't change the temperature. It changes the bonds from tight crystalline bonds to something a little bit looser. The cohesive bonds of a liquid. All right. It takes for H2O ice, it takes 80 calories per gram. So every gram of H2O ice has a certain number of crystalline bonds. Every bond requires a certain amount of energy to break apart. And therefore, every gram to melt requires a certain amount. And that's what we call the latent heat of fusion. Side note, latent heat of fusion is also the amount of energy cane that you must extract from liquid water to freeze it. So if you have some water at 273 Kelvin, liquid water, you've got to cool it 80 calories per gram. You've got to remove that. And how do you do that? Well, what you do is you put it in the freezer, and the freezer cools it off. The water's basically heating up the freezer, and then the little motor and the compressor and stuff remove that heat from the system and cool the freezer, keep the freezer cooled off and stuff. So eventually you're extracting all that heat from the liquid water, 80 calories per gram. And when you do that, you get a gram of ice. When you do enough grams, you get a bunch of ice cubes, right? So you can extract 80 calories to freeze a gram of liquid water. Yeah, so it'd be negative 80 calories. Yeah, so I mean, if you were, yeah, you could do it the other way. If I gave you some water at 290 room temperature and asked you to freeze it to 268, you'd have to extract. So all your Qs would be negative. Your delta T's would be negative, and you'd have to extract this much latent heat. Cool, freeze, cool. Yeah, you could do it that. But we're just going to be doing heat, melt, heat. Ashley, you had a question.
I was just about to ask that.
Okay, good.
You did it in the opposite direction if it didn't need it.
Yep, you can do it in the opposite direction. All right. Now, once you've melted, you put so many 80 calories per gram, however many you got. So in this case, 560 calories. All right, you've got it all melted, but it's still at 273. Now you've got to heat it up from 273 to whatever your target temperature is. In this case, the target temperature is 276. Right, so that's another 3K. Right, but you still use, for this part, the energy to heat up the liquid water by 3 kelvins. You use Q equals MC delta T. But now you use a different specific heat, 1.00, because you're working with liquid water. Right? So here's the basic information. And in between the initial and the final temperature, don't forget you have to melt. And the melting all happens at a constant temperature. So your pump, you got your propane burner, and you're pumping calories of energy into your sample of ice, and you're heating it up, and then you start melting, and you notice when it's melting, the temperature doesn't change. So if you have a thermometer stuck into it, you'll see the thermometer rise to 273, and then it'll stay there until all the ice is melted. And then once all the ice is melted, then it starts to increase again. Right? Now let's do the calculations. Right? So let's go through this. I cleared out the concepts, and let's just look at the equations now. Right? The concepts are the hard part, really. I mean, you can hire an engineering major to do all these calculations, but thinking the concepts, that's the hard part. Anyway, for heating the ice, yes, 7 grams, and it's ice, H2O ice. So the specific heat, David, is 0.50 calories per gram Kelvin. All right, so that's good. And then the delta T is 5 kelvins, because you're going from 268 up to 273. All right? So now notice here in this calculation, grams in the first parenthesis cancel grams in the denominator of the second middle parenthesis, specific heat. Similarly, Kelvin in the third parenthesis cancels Kelvin in the denominator of the middle parenthesis. So you're left with calories. Grams and kelvins cancel. That's what we want. So calories an element or a unit of energy, and so we've got calories. And it works out to 17.5 for this example. Now you might have had 2 grams of ice and final temperature 283. Then the numbers are going to work out differently for that. But for this one, for this example, yeah, 17.5. All right, melting the ice. This one's the easy one. Just take how many grams you have. Every gram of ice requires 80 calories to bust it apart into a liquid at 273. So 7 times 80, 560. We're talking a walk in the park here. And then, all right, now it's all melted. You've got 7 grams, but it's at 273. You want to get to 276. Another 3 Kelvin, Q equals MC delta T. 7 grams for the mass. 1.00. Now you're working with the specific heat of liquid water. 1.00 calories per gram Kelvin. And then your delta T. And that gives you 21. So your final answer here is 598.5. And what you want to do in web courses, I guess I've kind of come to the conclusion that it rounds 0.5 up to the nearest whole number. So you type in 599 for the answer on this example. So let me give you a couple tips that you can write down. In a heat melt heat, you're working with a heat and then another heating situation. So the specific heats are going to be different, potentially. In this case, 0.5 and 1.0. We're never going to do a heat melt heat cane where the mass changes. So we're going to be doing this inside of an enclosed container. So the mass will be the same. Somebody else might, like in the chemistry department, something evaporates, then you have a different mass. But we're going to just do gram for gram. We're going to keep the same number of grams. But delta T's, you might be working with two different delta T's. This one, the first one was 5 Kelvin. The second delta T, the second heating process, was 3 Kelvin. So depending on what your initial temperature is, what your phase transition temperature is, and what your final temperature is, you're going to have a couple different delta T's. All right. So it's, as I mentioned in the previous lecture, I'll mention again, Lexi, and that is that it's a lot of things to put together. And you've got to put them together in the right combination. And that's why it's a brain burner. But it can become a brain burner that you can crush with impunity. And hopefully with the homework over the weekend, extra practice. By the way, the mini review homework, you're going to have an hour to work on it, and you're going to have 6 attempts. So you get an extra practice. All right, questions about this problem, the heat melt heat? Yes. I got the Mountain Dew coming up. Hold your question. Nicole. From the initial temperature given, 268, the phase transition temperature, 273, the melting point, freezing point of water, and then the final temperature. And all those they're basically designed by me. Well, the phase transition temperature, 273, that's a constant of nature. But, on this heat melt heat, I choose the final and the initial temperatures, whatever I decide I want it, okay? And then I decide on how many grams to give you, so it might be 200 grams or, 2,500 grams or anything I want, okay? Another question. Okay, let's keep going. Question 13 about Mountain Dew. And I received some comments in office hours and in discussions and in messaging about this one. Dr. B, what am I doing wrong? And actually, question 8 is the key to question 13. And because question 8 goes through the concept of a food calorie being 1,000 of the regular thermal calories, right? And every thermal calorie is 4.184 joules, right? So one food calorie is 1,000 thermal calories, the little ones. And so one food calorie is 4,184 joules. Right? So every thermal calorie is 4.184 joules. So 1,000 of those are 4,184 joules. So that's and it's not a big deal. I just wanted you to trot through the calculation once. Huh? Yeah, so this is the equivalent of one food calorie. The second line, 1,000 thermal calories. Third line, 4,184 joules. So every calorie of Mountain Dew, every food calorie of Mountain Dew, multiplied by 4,184. So every answer that you have on number 13 is going to be some multiple of 4,184 joules. Okay, so it's going to be a ginormous number. Elizabeth. One thermal calorie is 4.184. One food calorie is what we've got in the yellow box. 1.000 food calories is either 1,000 thermal calories or 4,184 joules. Right? Yes? It's already multiplied in there. 1,000 thermal calories times 4.184. So what you could do is do this. 159 times 1,000 times 4.184. And that'll be your answer. Or you could do just 159 times 4,184. And you get the same number. And that's what this yellow box tells you. Right? So for every food calorie, multiply by 1,000. That'll give you how many thermal calories. For every food calorie, multiply by 4,184. That'll tell you how many joules. Okay, let's keep going. I want to talk about heat transport because we want to talk about thermal equilibrium today. Excuse me. There are three modes of heat transport, and all three of them are actually illustrated in this picture. A fire breather. You know, I don't know where it is, down in Mardi Gras, New Orleans or something like that. And the three modes of heat conduction, the first one is called, the three modes of heat transport, the first one's called conduction. And that's where you have a physical contact of some kind of hot with cold. So the heat flows into the colder object relatively easily. And it raises the temperature of the cooler object, and the stuff that's originally hot cools off a little bit. Now, for instance, the fire breather, he can't have kerosene in his mouth that's already on fire. So it's got to be liquid kerosene. He blurts it out of his mouth, and then he touches. See that little hand torch that he's carrying? The reason he does that is the stuff that he blurps out of his mouth, he's got to touch it at least a little bit with that hand torch. And then those droplets will all start burning. And he gets this cool effect. All right? Now, a counterexample to that is an insulator. Right? So a poor conductor of heat is an insulator. Here's a good insulator, air. And actually, in this picture, that fireball that you see in the upper left of the picture, that's surrounded by air. The air is not conducting very much heat. Air is a really good insulator. So if you have a fleece, a jacket, or a down jacket, or a down comforter or something, the reason those keep you warm, and not that a lot of people have that kind of equipment up here, but not too far north of here, you definitely want to have a fleece jacket in the winter, maybe a down comforter. They trap air. The fibers of the fleece jacket trap air, and the air is what's the insulator. The down inside the comforter trap air, very small pockets of air. And that air prevents heat from going from point A to point B. It's a good insulator. Here's another example. Stainless steel is a fairly poor conductor of heat. That's a special kind of a steel alloy, stainless steel. Whereas regular steel is a fairly good conductor of heat. If you go to the beach and you take your sandals or your sneakers off and you walk barefoot across the beach in the middle of the day, your feet are going to get burned by the hot sand because the sand conducts heat into your feet. Whereas the surrounding air might be the same temperature, but it's not going to feel as hot Here's a third example. If you take water, liquid water at 100 degrees Fahrenheit and air at 100 degrees Fahrenheit, and you put your right hand, you're in a 100 degrees room, so that air temperature is 100 degrees Fahrenheit, and then you put one of your hands into 100 degrees water, your hand is going to feel a lot hotter because the water is a good conductor of heat. Okay, it's going to conduct heat into your hand and your body's made of water mostly. So water's it's not like, it's not super, super good, but it's definitely better than air. Which is why, here's something that does happen here in Florida a lot. Raise your hand if you've ever done any scuba diving. Okay, that's a fair number of you. Now, if you do scuba diving or even surfing, even here in Florida, a lot of people wear wetsuits. And a wetsuit is to insulate your body from heat loss. You have that neoprene layer or some kind of foam layer and even if the water temperature is 75, you can perish from hypothermia if you're in the water long enough. And the deeper down you dive, the colder it gets. So you definitely want to have insulation. Second mode of heat transport, convection. Convection is considered heat transport because it's the bulk motion of a hot blob of something from point A to point B. So if conduction is not really rapid, you can get bulk motion. And that's what's happening with this fire breather. The air is not conducting much heat at all. A little bit, but not much. And because of that, and because something hot like the fireball, it's usually less dense than something that's cool, it's going to be buoyant. It's going to have a buoyancy force upward. And just like bubbles, if you're at the pool and you blow air out from your nose or from your mouth, and the bubbles will go straight up. If you're scuba diving, the bubbles from your regulator go straight up to the surface, right? If you take a bottle of shampoo or a bottle of pancake syrup and you tilt it upwards, a bubble will go to the top, kind of slowly, depending on how thick it is. Because there's buoyancy. Same thing with this. The heat makes it buoyant, and therefore the fireball rises upwards. So the hot stuff goes from point A, the initial point, upwards to point B. And that's considered heat transport. Convection. The surface of the sun is loaded with convection cells that are ginormous, many hundreds of miles across. Sun is big, and the convection cells are ginormous. But it's just like a boiling pot of water. You can see convection, when the water's boiling, if it's an open pot. The same thing here. Something I mentioned last time, the Yellowstone mantle plume. Yeah, rocks don't conduct heat very well. All right, so if the rock is fluid, like molten lava, magma, then a super hot blob of magma is going to tend to convect upward through the cooler magma. And it's not like it's moving at 80 miles an hour. It's pretty slow. It takes thousands and millions of years for the lava to rise, but we know that it's there, and we know that lava is rising to the surface at Yellowstone National Park, the Yellowstone mantle plume. Okay, so that's convection. So depending on what system you're in, and even water will convect. The oceans of Earth, all the currents like the Gulf Stream, and all the weather is all controlled by the currents in the oceans of the Earth. And most of those are driven by density. In other words, by convection. So it's pretty cool. Third mode of heat transport is radiation. And by that I mean electromagnetic radiation. Actually, those fireballs were glowing hot. They were glowing. They were losing energy, not much, but they were losing energy by electromagnetic radiation. Every photon of light from the surface of that fireball carried momentum and kinetic energy from point A to point B, somewhere outside. All right. Here's an example of it. If the material absorbs, whether it's ultraviolet, infrared, X-rays even can heat stuff up. If it absorbs it, it'll heat up the substance that absorbs it. So, for instance, your skin cells stop ultraviolet from the sun, unless you have sunblock on. But if you don't, you get sunburn. It causes a chemical reaction in your skin cells. And that stuff's not... The astronauts up on the surface of the moon, they need deluxe shielding because there's no atmosphere on the moon. So you just get all the solar radiation that starts at the surface of the sun. Boy, you get every bit of it if you're on the surface of the moon. Whereas the atmosphere of Earth blocks a lot of X-rays and ultraviolet. We get a little bit of it comes through. But our atmosphere is actually helpful. There's no atmosphere on the moon, so those guys, and even when they're in space, they have to be shielded as well. Now, the reason for that is something that we've measured, and it's called the solar constant. It's about 1,370 joules per second. So every square meter, so if you could go above the atmosphere, like 100 miles, 200 miles, where most of the atmosphere is below you, and you took a 1 square meter solar cell that could convert all of the solar energy to electricity, you'd get about 1,370 joules per second. And my wonderful students, side note, 1 joule per second is also known as a watt, W-A-T-T. A kilowatt is 1,000 joules per second. Whether it's transmitted or used, if you use or you transmit a certain amount of energy per second, in the metric system, it's measured by watts or kilowatts. Question? What's that? The question up here in the front was, why doesn't the moon have an atmosphere? The reason the moon doesn't have an atmosphere is because gravity is so weak. It used to have some, we think, a little bit, but it's not strong enough to keep a hold of it. The escape velocity is small enough on the moon that, all those random motions, all that kinetic energy, eventually it all just goes off into space. It's not strong enough to hold. Yeah, gravity. And Mars is pretty weak as well, and it doesn't have much left. It used to have more atmosphere, we think, billions of years ago. But Venus is big enough. Venus is a little bit smaller than the Earth, and it's big enough to hold a very dense atmosphere. But Mercury, no atmosphere there. Jupiter and Saturn, ginormulous. Plenty of atmosphere, very thick. Side note, spacecraft, satellites, they want to defeat, so you don't want your spacecraft to get cooked, and it will get cooked. So what they do is they clad the sides of a spacecraft with reflective mylar. That's very common. Or sometimes they just paint it white. Another way to defeat it is by, if you're, like, for instance, a spacecraft, an Apollo spacecraft going to the moon, they do what they call the barbecue roll, and that's a very slow roll. They're like corkscrewing forward. But it's very slow, but it's just fast enough so that one side of the Apollo spacecraft doesn't bake to a crispy crunch. It just keeps, rotating around and getting a little bit of heat and then cooling off on the dark side and then coming back around, getting more heat. So the space You know, the astronauts have to be very tightly shielded, and they want to defeat the solar heat gain. And here's another example. They have a gold visor. You know, they have a clear glass visor, or clear plexiglass maybe, I guess. But it's coated with a very thin layer of gold. You can just barely see it in this image. And it reflects a good amount of the solar heat energy. Aircraft pilots for the military that are in like these spy planes and stuff that go at really high altitudes, they also have to have gold-plated visors so that they don't fry their eyeballs, among other things. But some applications, you don't want to defeat solar heat gain. So like this thermal energy collector from the roof of your house, yeah, you want that to absorb. So it just depends on the situation, the task that you have before you. On the moon, your task is survival. Here in Orlando, you might have a task of getting solar energy to heat up your water. And then you want to have nice, transparent materials like this. Okay, now before we continue, let me pause for questions. Ashley.
Is there a mode that's more efficient than the others, or?
The question from Ashley up front is there a mode that's more efficient than others? And the answer to that is yes, no, maybe. In other words, it depends on the material that you're in. In the surface of the sun, inside the sun, there's a layer that's conducting, the energy goes outward, straight outward. But then the outer surface of the sun has big, huge convection cells, thousands of miles across. And same thing with water. You know, water might, under certain conditions, it might prefer to convect. Other conditions, it might just be really good at conducting and no convection. So it just depends. So yes, no, or maybe. It depends on the system that you're looking at. All right. Here's one that I was thinking about yesterday. I was thinking about brake lining, you know, for disc brakes. And what they do is disc brakes, they work this way. The part of the wheel comes in contact with the brake, and by friction, you create heat, and all the kinetic energy of your car is dissipated as heat. And that requires a substance that will heat up and conduct heat away from the surface of the brake. So you have a thin layer of like Kevlar or carbon fiber or some kind of metal, composite metal. And then behind that is a regular piece of steel that conducts the heat away from the surface of the brake disc. So it just depends on the device or the system that you're looking at. For instance, the sun, the surface of the sun, once the energy gets to the surface of the sun, everything is electromagnetic, radiative heat transport. But inside the sun, you got conduction and convection as well. So it's kind of cool. You just got to study it to see what's going to be more efficient. All right. I want to go through a calculation with you for the last 20 minutes of class, and it's going to be in your homework, and it is a deluxe brain burner type calculation. This is the thermal equilibrium calculation. We're going to mix two substances at different temperatures. You know, if you have a cup of coffee and you put an ice cube in it, it'll cool the coffee down, and it'll actually warm up the ice and then melt it. And so that's the kind of thing that we're going to do. Or, let's see, if you have a hot cup of coffee and you put a little bit of cream, you know, in it, it'll cool the coffee down just a little bit. Unless you put a ton of cream in there. Or if you put some ice cream in, ooh, a cup of coffee with some ice cream, that's more like Starbucks. You know, like, You know, when I go to Starbucks, I just get coffee. I don't get all those macchiatos and all that stuff. Man, those things are more like desserts. Anyways, let's do a mixing example. Let's not talk about Starbucks. I haven't had lunch yet. So what we're going to do is take two hypothetical substances, substance H, a small blob of that, and substance S, a bigger blob of that. Substance H is going to start at 333 Kelvin, pretty hot, it's yellow. And substance S is going to be initial temperature 288, so it's going to be cooler. And we're going to say that each one has a different specific heat. So the specific heat, C subscript H, is 1.2 calories per gram Kelvin. And these are hypothetical substances. I just used round numbers and, you know, whole number of temperatures and stuff, just so we have something to calculate with. But you're going to do a coffee cup calculation for homework. Similarly, specific heat for substance S, 1.4 calories per gram Kelvin, right? So this being the case, two different specific heats, if they trade the same number of calories gained or lost, you know, the hot one is going to lose calories, the cool one is going to absorb calories, but because they have different specific heats, they're going to heat up more. You know, one's going to heat up more. Which one's going to, gram for gram, which one's going to heat up more easily? Substance H or substance S? Substance H, because it has a smaller specific heat. Only 1.2 calories for every gram. It gives you 1 Kelvin. For substance S, 1.4 calories, just a little bit more. Right? Now, so you get different temperature changes, and on top of that, we're going to say that each substance has a different mass. So we're going to have less of one, more of another. All right? So I just chose two different nice round numbers, 40 grams for substance H. So we're going to put a dash of substance H into a bigger amount of substance S, 75 grams for substance S. And this is another reason that there's going to be a different temperature change. Even if something's easy to heat up, if you have a lot of it, you know, 1 calorie is not going to heat it up very much, even if it's easy to heat, if you've got a lot. You know, so something like gold, if you have a lot of grams of gold, even though gram for gram it's easy to heat up compared to water, if you got a lot of gold, I mean, it's not going to heat up very much. All right. Now, here's the concept that is going to bring it all together that we're going to use to figure out equilibrium. If they're at different temperatures, the hot substance will lose energy and the cool substance will gain it. Now, we're assuming in this particular example that we're in an insulated styrofoam container. So we're not losing energy to the outside world. We'll keep whatever energy we have is self-contained. All right? So if substance H loses 200 calories, substance S is going to get it. It's not going to go anywhere else. It's only going to go into substance S. All right? So here's a calculation. You know, let's say that substance H loses 200 calories. Well, that's going to be 40 grams times 1.2 calories per gram Kelvin times whatever delta T is. Now, we don't know what that is, but we can figure it out. And here's the kicker. If H loses 200, so QH is negative 200 calories, then QS is positive 200 calories. All right? Because it doesn't disappear into the outer universe. It's contained inside of our container. So energy is not being lost. It's all there. It's just rearranging. Now, what we're going to do next is a talking PDF, and we're going to Can you, not yet, sorry. We're going to do a talking PDF on the document camera. I'm going to pause the podcast, or pause the YouTube, and we're going to work on the document cam, and then by the time we're done with that, we'll be at the end of class. We'll dismiss. So let me pause. Now you can go to the document camera. See if I can get my clicker here. There we go. So there's our strategy. Try a different delta T.
After the homework 12, the mini study homework you
Yeah.
said? Is that
That's
for
going to light up at 1 o'clock tomorrow.
Is that for
Yeah, it's a regular homework. It's just more of a review instead of, like 12 is going to be just stuff from today.
Okay. What time? So it's 4 to 6.
I believe so.
And then do you know where it is? Where is the essay session for the review tonight?
Check discussions. I think it's downstairs, but I posted it in discussions, or she posted it in discussions.
Thank you.
Go ahead and check it
How
there.
do we know the stuff is gonna cool down quicker again?
Because, yeah, no, the homework is to figure out
Okay.
the equilibrium temperature.
All right.
right?
Thank you so much. Have a
You
good
are
one.
welcome.
I wanted to introduce myself. I'm Reagan.
Oh, hi.
I'm in this class, but like I've fallen really behind.